Segment 1. Definition and location of falls. Welcome to Civil Engineering Edge, where we break down complex engineering topics into easy and informative lessons. Today's video explores an essential component in irrigation engineering: Canal Falls. If you've ever wondered how irrigation canals handle sloping terrain without causing erosion or damage, then this video is for you. Definition: a canal fall is a hydraulic structure constructed on an irrigation canal to lower the water level gradually while dissipating excess kinetic energy. It is primarily used in sloping terrains to manage the difference in ground elevation along the canal alignment. Without canal falls, water flowing through steep stretches would gain destructive velocity, potentially causing scour, embankment failure, or excessive sediment transport. Location: canal falls are strategically located where the natural slope of the ground is steeper than the permissible bed slope of the canal. There's a requirement to transition between higher and lower reaches of the canal without increasing the embankment height. Near structures like head regulators, cross-drainage works, or branch canals, command areas need uniform supply despite elevation variation. In essence, a canal fall protects the canal section and ensures controlled water delivery. Proper placement of falls increases the efficiency of the irrigation system and ensures safety. In countries like India with vast and varied terrain, these structures are critical to long-term agricultural productivity. Segment 2. Types of falls. Canal falls are classified into several types based on design, function, and discharge range. Let's briefly explore the most commonly used ones. 1. Simple vertical drop fall. A basic structure where water drops vertically over a masonry wall, suitable for low discharges and moderate heights. 2. Trapezoidal notch fall. A fall with a trapezoidal notch that improves water passage and energy dissipation. Best for low to medium discharges. 3. Sarda type fall. Developed in the Sarda Canal project. This fall includes trapezoidal notches with a horizontal crest. It's modular and highly efficient. 4. Straight Glacis fall. Features a sloped concrete floor glacis. The hydraulic jump forms on the stilling basin for energy dissipation. Suited for moderate to high discharges. 5. Inglis or Baffle fall. Designed for high discharges. This fall uses baffle blocks and a glacis to control high-velocity flow safely. 6. Siphon well drop. A compact structure where water drops into a vertical well and exits at a lower level. Useful in steep terrain or limited space. Each type has its own advantages based on site conditions, discharge capacity, and economic factors. Segment 3. Design principles of various types of falls. Designing a canal fall requires careful consideration of hydraulic, structural, and economic factors. The core design objective is to dissipate surplus energy and maintain a safe and uniform water flow in the canal system. Key design principles include: 1. Hydraulic efficiency. The fall must dissipate energy efficiently to prevent scouring of the canal bed. Hydraulic jump formation is a commonly used technique. For example, Froude number FR is evaluated to determine flow regimes. FR equals VGDF R equals a frac vs skirt GDF R equals GDV, where VVV equals velocity, GGG equals gravity, and DDD equals head loss and drop. The vertical drop between upstream and downstream is considered. The fall must match the natural ground slope difference without disturbing flow continuity. 3. Stability. The structure must resist uplift pressure, overturning, and sliding. Aprons and curtain walls are designed accordingly. 4. Transition. Smooth transitions inlet and outlet reduce flow turbulence. Transitions should follow curves to minimize velocity spikes. 5. Material and site suitability. Choice of RCC, brickwork, or stone masonry is made based on soil conditions, discharge, and budget. 6. Cost optimization. Falls must be economical while ensuring durability. Over-design increases cost, under-design invites failure. By following these principles, engineers ensure that falls are not only functional but also safe and durable. Segment 4. Design of Trapezoidal Notch Fall. The trapezoidal notch fall is widely used in minor distributaries and branch canals due to its simplicity and cost-effectiveness. Structure. It features a rectangular body wall with a trapezoidal notch at the center. The water passes through the notch, forming a stream that falls onto a downstream apron, where energy is dissipated. Design elements. Notch shape. The trapezoidal shape improves flow efficiency. The usual side slope is 1 horizontal to 2 vertical. Discharge formula. Q equals CLH3 to Q equals CDOTL, CDOTH3 halves Q equals CLH3, 2, where QQQ equals CCC equals coefficient of discharge 1.70 to 1.84. LLL equals crest length. HHH equals head over crest. Apron design. The stilling apron is provided with proper thickness and length. Floor protection includes curtain walls. Materials, mostly brick masonry or RCC, is used for cost and durability. Advantages: simple and quick to construct. Handles moderate discharges. Reduces energy loss efficiently. Ideal for flatter areas in plains. This fall is particularly useful in Indian irrigation networks like the Upper Ganga Canal system, where low-cost solutions with good flow control are needed. Segment 5. Design of Siphon. Well drop. A siphon well drop is used in hilly terrain where steep drops are present and space is limited. Working principle: water flows over an upstream crest and drops vertically into a cylindrical or rectangular well chamber. It then flows out through an outlet channel at the bottom. The fall dissipates energy due to turbulence within the well and through the exit channel. Design features: inlet crest, designed as a smooth curve to streamline water into the well. It avoids cavitation and vortex formation. Well chamber. Depth depends on the total vertical drop and width on flow discharge. The diameter is usually 1.5 to 3 meters. Outlet channel. Designed for smooth re-entry into the canal, reinforcement and toe walls are provided. Hydraulic considerations. Energy loss is calculated by Bernoulli's equation. Head loss is used to estimate the height of the well. Adequate freeboard and access openings must be included. Advantages: highly compact design, excellent energy dissipation, suitable for urban areas and sharp terrain drops. Though costlier than simple falls, the siphon well drop is essential in regions like Maharashtra's Western Ghats, where steep slopes make horizontal structures impractical. The remaining segments will continue in the next message due to length limits. You said, please write the remaining segments. ChatGPT said, certainly. Here's the continuation of the script for Canal Falls in Irrigation System, completing all remaining segments with the required detail and word count. Segment 6. Design of a simple vertical drop fall. The simple vertical drop fall, also called a rectangular drop fall, is one of the earliest and most straightforward fall structures in canal engineering. It's used in small distributaries where the difference in bed level is minor, typically up to 1.5 meters. Structure: water drops vertically from a raised rectangular crest wall and lands on a horizontal concrete or stone apron, where energy is dissipated. Side walls and training walls ensure flow stability. Design parameters: crest width B equal to the canal bed width or slightly larger. Height of drop H equal to the vertical difference between upstream and downstream canal beds. Apron design: length of apron is calculated using empirical formulas to ensure hydraulic jump formation. L equals 5 times D2. L equals 5 times D underscore 2. L equals 5 times D2. where D to D underscore to D2 is the sequent depth of hydraulic jump. Curtain walls, provided at the end of the apron to prevent piping and uplift pressure. Freeboard, additional vertical clearance to avoid overflow during peak flow. Advantages: inexpensive and simple, easy to construct and maintain. Effective for low discharge canals. Limitations: ineffective in high discharge or high drop zones. Limited energy dissipation compared to more advanced falls. Commonly used in India's minor irrigation channels. It remains a preferred choice in flat terrains like Uttar Pradesh and Punjab. Segment 7. Design of a Sarda-type fall. The Sarda-type fall is named after the Sarda canal system and is suitable for discharges up to 14 cubic meters per second. It offers improved flow regulation and energy dissipation over the simple drop fall. Structure: the Sarda fall has trapezoidal notches in a raised crest wall. The flow passes through these notches, and the remaining width carries water at normal depth. The downstream glacis with a masonry or concrete apron allows hydraulic jump formation. Design components: notch details, generally 1.5 to 2 meters wide and 1 meter deep. Side slopes are 122 v. Multiple notches are spaced evenly across the fall. Crest length equal to bed width of the canal. Discharge calculation: Q equals NCLH3 to Q equals NCDOTC CDOTL. CDOTH3 halves Q equals NCLH3. 2. Where NNN equals number of notches, LLL equals length, approximately equals 1.70 HHA. Stilling basin, designed to ensure hydraulic jump forms properly. Baffle blocks are often added. Materials, commonly constructed with brick or stone masonry with a concrete floor. Advantages: economical with modular construction. Greater discharge capacity, better flow distribution. Widely adopted in North India, especially in the Ganga Canal system, the Sarda fall balances cost, performance, and scalability, making it ideal for main and branch canals. Segment 8. Design of a straight glacis fall. The straight glacis fall is a modern structure designed for medium to high discharge canals. It features a sloped floor glacis instead of a vertical drop, providing a gradual energy transition. Structure: the upstream crest leads to a straight inclined concrete glacis, which drops the water to a stilling basin where energy is dissipated through a hydraulic jump. This design allows high-velocity flow to transition safely. Design elements: crest level, positioned slightly higher than downstream bed. Glacis slope, typically between 1 to 2 to 1 to 3 v/h depending on flow rate. Hydraulic jump location, calculated based on fruit number FR and downstream depth. Stilling basin and baffle blocks. The length of the basin is generally L equals 5 times D2 D2 equals sequentif L equals 5 times D underscore 2 quad. Text D underscore 2 equals sequent depth L equals 5 times D2 D2. Baffle blocks are placed to stabilize the jump and reduce turbulence. Curtain walls and protection works. Curtain walls are provided both upstream and downstream for seepage control. Riprap and stone pitching are used for protection. Advantages: superior energy dissipation, minimal turbulence, ideal for large irrigation channels. Used in India's Rajasthan and Madhya Pradesh projects, the straight glacis fall is ideal where water flow is high and needs efficient energy management with minimal downstream erosion. Segment 9. Design of a baffle fall or Inglis fall. The Baffle Fall, also known as the Inglis Fall, was developed by Sir Charles Inglis and is suitable for high discharges in major irrigation canals. Structure: it combines a glacis and a stilling basin with baffle blocks or teeth, which absorb the energy of fast-flowing water. This controlled hydraulic jump reduces downstream erosion. Design highlights, crest and glacis. Similar to the straight glacis fall, but followed by a more elaborate energy dissipation system. Baffle platform, located at sequent depth D. This platform supports the baffle blocks. Baffle blocks, placed in rows and sized based on velocity and depth. Their function is to increase turbulence and reduce kinetic energy. Stilling basin length. L equals 6 times D2 empirical formula. L equals 6 times D underscore 2 quad text empirical formula. L equals 6 times D2 empirical formula. Tail channel transition, designed to gradually return flow to normal depth. Safety features, curtain walls, drainage filters, and downstream pitching to prevent undermining. Advantages, highly effective for large volumes. Superior energy dissipation, ideal for erosion-prone soils. The Inglis Fall is widely used in Maharashtra's large canal systems, including Koyna and Krishna Basin projects. Though more expensive, it ensures safety, durability, and operational efficiency. Segment 10. Best fall uses, benefits, and cost efficiency for India. Each type of canal fall has specific use cases depending on terrain, discharge, and budget, especially in a diverse country like India. Best use cases, vertical drop and trapezoidal notch falls are perfect for minor canals in plains, offering low cost and easy maintenance. Sarda type falls are highly suitable for branch canals, offering modular and scalable designs. Siphon. Well drops excel in hilly areas, where steep drops and compact structures are needed. Straight glacis and baffle falls are best suited for main canals with high discharges, especially in large irrigation projects. Benefits: prevents erosion and structural damage. Improves water distribution across varying terrain. Ensures long-term safety and durability. Adapts to regional needs, be it Punjab's plains or Maharashtra's hills. Cost efficiency. Simple vertical and trapezoidal falls cost the least and require minimal upkeep. Sarda and glacis falls offer a balance of cost and performance. Baffle and siphon drops are costlier but necessary for technical and safety reasons in specific regions. In conclusion, canal falls are vital to India's irrigation infrastructure, ensuring water is delivered safely and efficiently across millions of hectares. Selecting the right type of fall ensures optimal performance and cost effectiveness. Thanks for watching. If you found this video helpful, like, share, and subscribe to Civil Engineering Edge for more insightful content on irrigation and infrastructure systems.